Hello everyone, my name is Lim Zhi Hang. I'm come from school SMK Taman Pelang Indah. I'm from class 4 scientist 1. My physics teacher is teacher Julaika. So today I want to talk about the KSSM Physics Form 4, Chapter 3 Gravitation, Subtopic 3.3, Man-made Satellite. First, as an introduction, so what will we learn in this subtopic? I divide into 3 parts, which is linear speed of satellite, escape velocity, and type of satellite. Before we start it, I talk about the unit in calculation, which consists of Newton, which we for force, and for distance or height we use meter. For mass we use kg. For speed we use meter per second, which here we got linear speed and escape velocity, which use meter per second. And time we use the hour. So first, what is satellite? Satellite is an object which orbits another body with or without a purpose. We call it as a satellite. So there are 2 types of satellite, which is natural satellite and artificial satellite. The natural satellite is well known is the moon. We call moon as a satellite because it orbits around a body which is our Earth, the Earth. Then another is artificial satellite, also called as man-made satellite. Here's an example of artificial satellite, which is Sputnik. The first artificial satellite is that launched to the outer space, and MESAT satellite system because it's of MESAT 1, MESAT 2, MESAT 3, and this is the satellite launched by Malaysia. So as our first part, we learn about the linear speed of satellite. So to find the formula for linear speed of satellite, we need to relate centripetal force and gravitational force, because satellite is in a circular motion. So, and a force you add to the object in a circular motion towards the center of the circle, because it is centripetal force. And based on Newton's universal law of gravitation, so the gravitational force exists between any 2 bodies, which also include between satellite and Earth. So centripetal force F equal to mv squared over r, which m is the mass, v linear speed, r radius of circle. Gravitational force F equal to g m1 m2 over r squared. F equal to gravitational force, m1 is the mass of first body, m2 is mass of second body, and r is the distance between center of both bodies, and g is the gravitational constant. Okay. So as we need to relate these 2 types of force, which is centripetal force equal to gravitational force between them. mv squared over r equal to gmm over r squared. Here we divide the same part with m and m, then r and r. We got v squared equal to gm over r, and lastly v equal to square root gm over r, which v is linear speed, g is gravitational constant, and m is mass of Earth. Lastly, r is the radius of orbit of satellite. Based on this formula, v equal to square root gm over r, we got gm is constant. Gm is constant, so v only depends on value of r, which is radius of orbit. Next is an example. Is for calculate the linear speed of the Global Positioning System satellite, GPS. As we know, we use the formula v equal to square root gm over r. First, we need to know the height, which is 20,200 kilometer. So we should change from kilometer to SI unit, which is meter, and use the standard form to represent. Second, find the value of r, which is big R plus height h, radius of Earth plus height of orbit. And we plus, then we got 2.657 times 10 to the power of 7 meter. Lastly, start all the value into the formula, which is
G, gravitational constant, M, mass of Earth, and lastly, value of R. We get it here. So we got the answer 3.x7 times 10 to the power of 3 meter per second. So if we use all the value here to unit to calculate, we will get the answer is in the form of square root Newton meter per kg. But as what I say before, for linear speed, we got the value is meter per second. Why? Because F equal to ma. Which Newton, for force is Newton, we can also make this as ma, kg meter per second square. Kg for mass, a meter per second for acceleration. Kg per kg. Meter times meter, meter square, and per second square. So square root Newton meter per kg also can become square root meter square per second square, which eliminate is to become meter per second. Next, move on to the second part, which is escape velocity. Escape velocity is the minimum velocity needed by an object on the surface of Earth to overcome gravitational force and escape to outer space. Actually, we know velocity, the minimum velocity needed by an object to escape to outer space by overcome the gravitational force. In order to find the value of escape velocity, we also can relate 2 times 2 formula, which is kinetic energy 1/2 mv squared, and gravitational potential energy U equal to negative -gmm over r. Escape velocity is achieved when the minimum kinetic energy of an object is able to overcome its gravitational potential energy. So we can say that minimum kinetic energy plus gravitational potential energy equal to 0, which also can say is minimum kinetic energy equal to gravitational potential energy. Eliminate the same with m, then v squared equal to 2gm over r, and lastly v equal to square root 2gm over r. This is the value for escape velocity, which actually is nearly same with linear speed, but just add a 2 here. This is an example to find the value of escape velocity. So first is about escape velocity from Earth, from Sun, and from Moon. We use the same formula. V equals to square root 2gm over r. 2 times g. G is gravitational constant, so it's constant, right? Then this is m, mass of Earth, mass of Sun, mass of Moon. R, radius of Earth, radius of Sun, radius of Moon. Then you get the answer. Escape velocity from Earth, 1.12 times 10 to the power 4 meter per second. From Sun, 6.18 times 10 to the power of 4, 10 to the power of 5 meter per second, and from Moon, 2.38 times 10 to the power of 3 meter per second. As we know, V equals square root 2gm over r. So we find that actually V does not depend on mass of object, which is the small n. Okay, we find that it depends only on the body is orbit around, or on the only. This here is the benefits and implication of escape velocity. First, Earth is able to maintain a layer of atmosphere around it. Why? Because molecules in atmosphere move at average linear speed 400 meters per second, lower than Earth escape velocity, which around 11,000 meters per second. Molecules are unable to escape to outer space. Second, commercial aircraft and fighter jets won't escape to outer space. So
Example, commercial aircraft is only 250 meters per second and fighter jets is 22,000 meters per second. So it's unable to escape to outer space because its linear speed is lower than Earth's escape velocity. Third is rocket launching. Due to the high escape velocity of Earth, so it requires a large quantity of fuel to produce high thrust that enable the rocket to achieve the Earth's escape velocity. Because the high thrust is pushed to the ground and based on Newton's first law of motion is aviation, there's a friction with same magnitude in opposite direction. It pushes back the rocket and pushes to the outer space. The function of rocket is actually turn the spacecraft into outer space. It's for Earth atmosphere. But here actually the satellite achieves the Earth escape velocity. This fighter jets with around 22,000 meters per second linear speed, and this is commercial aircraft around 250 meters per second. This is rocket launching, so it needs to produce a high thrust. So now we move to the third part of our learnings today, which is types of satellite. Satellite can be divided into natural satellite and artificial satellite. For artificial satellite, we can further divide into geostationary satellite and non-geostationary satellite. For geostationary satellite, or I call it as GSS, is in a specific orbit named geostationary Earth orbit. It's around 35,786 kilometers from the Earth's surface. And for non-geostationary satellite, I call it as NGSS, is on a lower or higher orbit than the geostationary Earth orbit. Okay. This now is an example like satellite A is a geostationary satellite because it's on a geostationary Earth orbit. It's always above X. If X is your house, so it's always above your house. Then this satellite B is in a part lower than a geostationary orbit. So we call it a non-geostationary satellite. You can also imagine there's a satellite C here. It's around the outer, so it's higher than geostationary Earth orbit. So it's also a non-geostationary satellite. The similarities of geostationary satellite and non-geostationary satellite is both of them orbit the Earth. And to calculate the value of linear speed, we use the same formula, which is V equal to square root GM over R. And for period of rotation is T equal to square root 4 pi squared R cubed over GM. Now we look about the differences. For GSS, is geostationary satellite. The direction of rotation is same as Earth rotation on its axis, which is from west to east in counterclockwise rotation direction. For NGSS, need not to be the same as direction of Earth rotation. As for time, GSS is same as the period of rotation as Earth is equal to 24 hours, and NGSS can be more than or less than 24 hours. As for location, is GSS always above the same geographical location, and NGSS is above different geographical location. So for GSS, the function is communication satellite. Why? Because it needs to be above the same geographical location, so it can help as in the communication. If the communication satellite can move faster, very fast, then maybe sometimes in the different press, then above some press, the non-communication satellite, so you can't communicate with others. The signal cannot be transferred. Example is MESA. When for NGSS, it can function as Earth imaging. It can move faster can take many pictures of
Earth, and GPS is global positioning system. It also need to be in different geographical locations so it can have an overall view of the Earth. And weather forecast is in different geographical locations so you can have many press weather. Example, Tiongsak, Rajasat, Pipit, and IS. Okay, this is first Malaysian satellite, MISAT. Tiongsak 1, the first Malaysian microsatellite. Rajasat, Malaysian Earth observation satellite carrying a high-resolution camera, is a NGSS satellite. Is ISS, International Space Station. Modular is a modular space station in low Earth orbit. Okay, so as a conclusion, we have learned three main things, which is linear speed of satellite, V equal to square root gm over r. Escape velocity, V equal to square root 2 gm over r. Third type of satellite, which is geostationary and non-geostationary satellite. Now we move on, let's do some exercise. So this exercise is based on textbook Formatives Practice 3.3. Question 2. What factors determine the linear speed of satellite orbiting the Earth? As we see, linear speed, so we know you need to use the formula V equals to square root gm over r. As gm is constant, so r is the factors determine the linear speed, which is radius of satellite orbit. Question 3. State two factors which influence the value of a escape velocity from a planet. Escape velocity formula V equals to square root 2 gm over r. As g is constant, so m mass of the planet and r radius of the body will become the factors that influence the escape velocity, which radius of the body is distance between the body to the center of the planet. Question 4. Discuss whether escape velocity from the Earth for spacecraft X of mass 1,500 kilograms is different from spacecraft Y of mass 2,000 kilograms. So we know escape velocity, we write out from here, V equals to square root 2 gm over r. Based on the formula, G is constant, so escape velocity of object only depends on the m mass of Earth and r distance of object from the center of the Earth. The escape velocity does not depend on mass of object, so the escape velocity are same, even though the mass are different. Question 5. Propa-1 satellite orbits the Earth at a height of 700 km. What is the speed of this satellite? Linear speed of this satellite. So it's given G, gravitational constant, mass of Earth, radius of Earth. Escape velocity, linear speed, we need to use the formula V equals to square root gm over r. As here got the height, so we need to plus h. Submit the formula G bm big M r plus h 700 km turns to meter. When we got the answer 7.504 times 10 to the power 3 meter per second. Next, we do the performance evaluation, which is also based on textbook. Question 2. Why does the linear speed of a satellite orbiting the Earth does not depend on the mass of satellite? Firstly, satellites fall freely around the Earth. Is fall freely around the Earth with a central acceleration equal to the acceleration of gravity. So the acceleration of gravity does not depend on mass of object. So
The linear speed also does not depend on mass of object. Next question 8. A spacecraft orbits the Earth at a height of 1,600 km. Calculate the escape velocity for the spacecraft. So we know the escape velocity. So we use the formula V equal to square root 2 gm over r plus h height. Submitting all the formula 2 gravitational constant, mass of Earth, radius of Earth plus height. Change to meter. From kilometer change to meter. Then we got 1.6 times 10 to the power of 6 meter. All the values sub in and times divide square root. You get 9.996 times 10 to the power of 3 meter per second. Okay, question 3. Question 9. Figure 5 shows planet Saturn with rings made out of small particles around it. Okay, it's over around it, right? Then Saturn has a mass of 5.6x times 10 to the power of 26 kg and radius of 6.03 times 10 to the power of 7 meter. Calculate the escape velocity of planet Saturn. Escape velocity, we use formula V equals to square root 2 gm over r. Sub in the formula, sub in the value, g gravitational constant, m mass of Saturn. Here, get the value here. Radius r, radius of Saturn. Then we got 3.54 times 10 to the power of 4 meter per second. B. Discuss the possibility of the small particles in the rings of planet Saturn escaping into the outer space. Is this possible? It's impossible for these small particles to escape because the escape velocity of the planet is very high. It's even higher than our Earth, right? Earth is only around 1.12 times 10 to the power of 4. Okay. Now question 11. Sorry. Table 1 shows information on 3 types of orbits X, Y, and Z for a satellite orbiting the Earth. So it's about the table. Orbits, so this is about the table. Orbit X, Y, Z, shape of orbit, height of orbit, orbital period here. So a space agency wishes to launch 2 satellites, which is P and Q, to orbit the Earth. Satellite P is an Earth imaging satellite that can capture image of various locations on the surface of Earth. Why? While satellite Q is a communication satellite. Use the information in table 1 to identify which orbits. Okay, this is suitable for satellite P and satellite Q. Expand your choice. Okay, so this is satellite Q. Satellite Q is communication satellite, so it's based on the information. Orbital period should be 24 hours. To rotate together with the Earth above the same geographical location and can receive and transmit communication signal to station on Earth. It should be the raw orbit, so its height from the surface of Earth is constant. And its height should be on the 3.59 times 10 to the power of 7 meter because it's on the geostationary orbit. So orbit Y is suitable for satellite Q, which is this circle 3.59 times 10 to the power of 7 and orbital period 24 hours. And for satellite P is an Earth imaging satellite. So there are 2 choices here, which is Z or Y, LX. So first, the shape of orbit is to be an ellipse, so we can have a far and cross photograph. Height of orbit should be lower, so it can take the picture clearly, and orbital period should be short, so it can be
in a various part. This satellite P is an Earth image. First, orbital height is small, so clear photograph of Earth's surface can be taken. Orbital period is less than 24 hours, so it can orbit the Earth several times a day. Satellite will be at different locations above the surface of the Earth and take photographs in many different places. Elliptical shape orbit, so near and far photographs can be taken. So orbit X is suitable for satellite P. Orbit X. Now this is one extra question. So which of the following statement is not true? Before that, we look at here. Which about the Earth orbit. We got consists of 4 types of Earth orbit, which is low Earth orbit, medium Earth orbit, high Earth orbit, and lastly, geostationary Earth orbit. As we see, the lower is from low Earth orbit, then medium Earth orbit, then geostationary Earth orbit, lastly, high Earth orbit has the highest height. Low Earth orbit, the orbital period is shorter than to medium Earth orbit, then to geostationary Earth orbit, then lastly, high Earth orbit. So the answer is B. Why? Because the height of high Earth orbit less than the height of medium Earth orbit. The height of high Earth orbit should be the highest already. So there's no other Earth orbit that can be highest than Earth orbit. So that's all from me. So today as a revision, as a conclusion, we learn linear speed, which use formula V equals to square root gm over r. Escape velocity V equals to square root 2 gm over r, and type of satellite, geostationary satellite and non-geostationary satellite. That's all from me. Thank you.